transfer of heat takes place in three different modes. They are thermal conduction, convection, and radiation. First, let us learn about thermal conduction. Thermal conduction is a mechanism of heat transfer between two adjacent parts of a body, or between two bodies in thermal contact because of a temperature difference. For example, observe the person holding an iron rod at one end and placing the other end in fire. One end of the iron rod, which is in the flame, at a high temperature, and the other end at low temperature. Heat flows from the hot end to the cold end by thermal conduction. And as a result, after some time the person drops the rod. When heat is supplied at one end of the rod, the molecules in hotter regions gain kinetic energy and start vibrating faster. These vibrations are passed on to neighboring molecules through intermolecular bonds. In this way, the energy is eventually transferred to the whole body. Thermal conductivity of a substance, which is usually referred to as conductivity, depends on the state and nature of a substance. In solids, metals are very good conductors of heat. This is due to two reasons. One is that the molecules are very closely packed and thus help transfer vibrational energy quickly. The second reason is that metals contain a large number of free electrons, which also contribute to the quick transfer of heat energy. The free electrons close to the heat source receive heat and move faster through the metal. During this process, they collide with molecules and other electrons and pass a part of their energy on to them. In the case of gases, the molecules are far apart and hence the exchange of energy among them is very difficult. Therefore, gases are very bad conductors of heat. In the case of liquids, the intermolecular space is more than in solids and less than in gases. Therefore, the conductivity of liquids is greater than that of gases, but less than that of solids. Now consider a metallic rod of length L and a cross-sectional area A. Let the two ends of the rod be maintained at two different constant temperatures, T1 and T2. These temperatures are maintained by placing one end of the rod in a steam chamber and the other in a chamber with flowing water. Temperatures T1 and T2 are maintained in such a way that T1 is greater than T2. The end of the rod where the temperature is T1 is hotter than the other. Let us also assume that the rod is fully insulated and there is no loss of heat to the surroundings. Heat starts flowing from the hot end to the cold end. And after some time, there will be a steady flow of heat through the rod. The rate of heat flow is defined as heat current H. If delta Q is the heat flowing across any cross-section in time, delta T, then heat current H is equal to delta Q by delta T. Let this be equation 1. In a steady state, the temperature of the rod decreases uniformly from the hot to the cold end of the rod. The change in temperature per unit length is defined as the temperature gradient. Since the change in temperature for a length of L is T2 minus T1, the temperature gradient is expressed as T2 minus T1 by L. Let this be equation 2. It is experimentally found that in a steady state, heat current H is directly proportional to the temperature difference between the two ends and cross-sectional area of the rod. It is also found that H is inversely proportional to the length of the rod. That is, H is equal to delta Q by delta T, which is equal to Ka into T1 minus T2 by L. Let this be equation 3, where K is the proportionality constant and is called the thermal conductivity of the material. The SI unit of thermal conductivity is joule per second per meter per Kelvin or watt per meter per Kelvin. For a rod, the mathematical expression L by Ka is defined as its thermal resistance R, where L and A are the length and cross-sectional areas of the rod respectively, and K is the thermal conductivity of the material of the rod. Now, equation 3 can be written as heat current H is equal to T1 minus T2 by R. Let this be equation 4. Equation 4 is identical to Ohm's law of current electricity. This identity can be extended to some other cases as well. For example, if two rods of thermal resistances R1 and R2 are connected in series, then the equivalent thermal resistance R of the combination is expressed as R is equal to R1 plus R2. On the other hand, if they are connected parallelly, then the equivalent thermal resistance of the combination R can be found using the relation 1 by R is equal to 1 by R1 plus 1 by R2. Now consider two bars each of length L and a cross-sectional area A. The bars, made of different material of thermal conductivity K1 and K2 respectively, are soldered end to end, and the free ends are maintained at two different temperatures T1 and T2, with T1 greater than T2. In a steady state, heat current in the first rod is equal to heat current in the second rod. If the junction temperature is T0, then K1A into T1 minus T0 by L is equal to K2A into T0 minus T2 by L, or K1 into T1 minus T0 is equal to K2 into T0 minus T2. The junction temperature T0 is equal to K1 T1 plus K2 T2 by K1 plus K2. Since heat current through the combination is equal to heat current through the first rod, if the equivalent thermal conductivity of the combination of two conductors is K, then we can write Ka into T1 minus T2 by 2L is equal to K1A into T1 minus T0 by L. On simplifying, we get K into T1 minus T2 is equal to 2K1 into T1 minus T0. Substituting the value of T0, we get K into T1 minus T2 is equal to 2K1 into T1 minus K1 T1 plus K2 T2 by K1 plus K2. On further simplifying, we get K into T1 minus T2 is equal to 2K1 into K2 into T1 minus T2 by K1 plus K2. Therefore, K is equal to 2 K1 K2 by K1 plus K2. This is the expression for equivalent conductivity when two conductors are connected in a series. The table shows the thermal conductivities of some materials. Metals have very high thermal conductivities and hence conduct heat rapidly. Materials like wood, bakelite, and wool are bad conductors. When loss of heat by conduction is to be restricted, the body must be surrounded by an insulating substance. For example, we use woolen clothes in winter to prevent loss of heat, as the air is entrapped in the pores of the wool fabric, which acts as an insulator. When heat is to be transmitted faster, good conductors are used in the process. For example, cooking utensils, water coolant systems in car radiators, and nuclear power plants all use good conductors. Let us conduct an experiment to understand what is meant by convection. Take some water in a container and heat it by placing it on a burner. The bottom of the container absorbs heat from the burner and then conducts it into the water. Since the entire water body is not in contact with the bottom of the container, all the layers of water cannot absorb heat by conduction. The water that is in contact with the bottom of the container absorbs heat by conduction, and its temperature increases. Because of a rise in temperature, this part of water expands, and as a result, its density decreases. This low-density warm water is lifted up towards the surface due to buoyancy, and the denser cold water moves down and comes into direct contact with the hot base of the container. Once again, the water in contact with the base of the container becomes hot and is replaced by a colder part of the water in the container. This way, all the water gets heated. Heat transfer by actual motion of matter from one region to another is known as thermal convection. Since convection involves bulk movement of different parts of matter, this mode of heat transfer is possible only in fluids. Thermal convection can be natural or forced. If the convection is caused by difference in density due to thermal expansion, then it is called natural convection. The heating of water is an example of natural convection. Gravity plays an important role in natural convection. That is why, in natural convection, heating is always in the upward direction. If the container is heated at the top, transmission of heat by convection does not take place in the downward direction. Natural convection is responsible for many day-to-day phenomena. For example, In coastal areas, wind blows from the sea to the land in the daytime. This is known as sea breeze. The sea water warms up slower than the land because of high specific heat capacity of water. As a result, the air above the land becomes hotter and moves up, creating a low pressure area. Now, the air above the sea water moves towards the land and forms the sea breeze. During the night time, exactly the reverse process takes place. Air moves from the land to the sea. This is known as land breeze. Trade winds are another example of natural convection. The steady surface winds blowing from the northeast and the southeast towards the equator are called trade winds. The equatorial region receives more heat energy than the polar regions. Air at the equatorial region is much hotter than the air at the polar regions. In the absence of any other effect, the air at the equator rises and moves towards the polar regions and descends at the poles. The cold air from the polar region moves towards the equatorial region, forming convection currents. But because of the Earth's rotation, air at the equatorial region moves with a speed of 1,600 kilometers per hour in the eastward direction, whereas the speed of these winds is almost zero at the poles. These two movements of air, one because of convection and the other because of the Earth's rotation, result in trade winds. In the northern hemisphere, instead of descending at the North Pole, the air descends at 30 degrees north latitude and moves towards the equator. Similarly, in the southern hemisphere, instead of descending at the South Pole, the air descends at 30 degrees south latitude and moves towards the equator. Let us now discuss forced convection. If the movement of matter is caused by a pump or blower for transfer of heat, it is called forced convection. Let us look at some common examples of forced convection systems. One of the most common examples of forced convection that we see around us is the working of a hairdryer. Air at room temperature is sucked by a motor and heated up by forced convection as it passes over the hot coils inside the dryer. This hot air is then blown out through the nozzle provided. The human circulatory system is another example of forced convection. Blood is forced through the circulatory system by the heart to maintain the required uniform temperature throughout the body. The third mode of heat transfer is thermal radiation, where heat is transmitted even through vacuum in the form of electromagnetic waves. The electromagnetic waves emitted by a body by virtue of its temperature is called thermal radiation. Heat energy received from the sun is in the form of radiation. Like any other electromagnetic waves, thermal radiation can travel at a speed of 3 × 10⁻⁸ meters per second. In fact, all bodies emit thermal radiation. The rate of emission of thermal radiation depends on the temperature of the body. When thermal radiation falls on a body, it is partly absorbed and partly reflected. The amount of heat absorbed by a body depends on its color. Black bodies have a greater capacity of absorbing radiant energy. This is the reason why we wear light-colored clothes during summers and dark-colored ones during winters. A thermos flask is designed to minimize heat loss by all the three modes of heat transfer. This consists of a double-walled, evacuated glass vessel, with its inner and outer walls coated with silver. The vacuum between the two walls prevents heat loss by conduction and convection. The silver coating on the walls prevents exchange of heat by radiation. Therefore, heat transfer is minimized by controlling conduction, convection, and radiation. It is a common phenomenon that a hot body exchanges heat with its surroundings and cools. The heat lost by the body to its surroundings per unit time is called the rate of cooling of the body and depends on several factors. Let's conduct an experiment to study the factors that influence the rate of cooling of a body. Let's take some water at room temperature in a calorimeter and place in it a thermometer. If the temperature of the water is T1 degrees Celsius, then the temperature of the surroundings is also T1 degrees Celsius. Now, let us first heat the water in the calorimeter to raise the temperature to say T2 degrees Celsius. And then stop heating and allow the water in the calorimeter to cool. Start a stop clock and note the temperature T2 of the water at regular intervals, say after every minute. The difference in temperature between the water and its surroundings is expressed as delta T, which is equal to T2 minus T1. Delta T can be computed for each value of T2. When a graph is plotted by taking delta T along the y-axis and time t along the x-axis, we get a curve. The graph indicates that the cooling of water depends on the temperature difference between the water and its surroundings. The greater the temperature difference, the greater the fall in the temperature of the hot water. With the passage of time, the temperature difference between the hot water and its surroundings decreases, and hence the change in the temperature of the water also decreases. Newton made a systematic study of the cooling of different bodies and proposed a law known as Newton's law of cooling that holds good for small differences in temperature between a hot body and its surroundings. Newton's law of cooling states that the rate of heat lost by a body is directly proportional to the difference in temperature between the body and its surroundings. If a body is at a temperature T2 degrees Celsius and its surroundings are a temperature of T1 degrees Celsius, where T2 is greater than T1, then the rate of loss of heat is expressed as minus dQ by dt is proportional to T2 minus T1, or minus dQ by dt is equal to K into T2 minus T1. Let this be equation 1. where K is the proportionality constant, which depends on the area and nature of the body. Let the mass of the body be m, whose specific heat capacity is S, at an initial temperature T2, with its surroundings at a temperature T1. If the temperature of the body is changed by delta T2, because of a small loss of heat delta Q, in a small interval of time delta T, then delta Q can be expressed as a product of M, S and delta T2. Then, the rate of heat loss is equal to delta Q by delta T equals to M, S delta T2 by delta T. Let this be equation 2. But according to Newton's law of cooling, we have minus delta Q by delta T is equal to K into T2 minus T1. Let this be equation 3. Combining equations 2 and 3, we get minus ms into delta T2 by delta T is equal to K into T2 minus T1. Or delta T2 by T2 minus T1 is equal to minus K by ms into delta T. Let this be equation 4. Taking limits on both sides, we get dT2 by T2 minus T1 is equal to minus K by ms into dt. On integrating this expression on both sides and simplifying, we get log to the base e T2 minus T1 is equal to minus K by ms into T plus C. Let this be equation 5. This can also be written as T2 minus T1 is equal to e to the power minus K by ms into T plus C, which is equal to e raised to the power C into e raised to the power minus K by ms into T. Let this be equation 6. If we define K equal to K by ms and C equal to e raised to the power C, then equation 6 becomes T2 minus T1 is equal to C into e to the power minus kt, or T2 is equal to T1 plus C into e to the power minus kt. Let this be equation 7. This equation can be used to calculate the time taken for a body to cool through a particular range of temperature. The law is applicable to small temperature differences. Even when the transfer of heat is due to a combined effect of conduction, convection and radiation, the rate of cooling is proportional to the difference in temperature. For example, if a beaker of hot water placed in surroundings whose temperature is 25 degrees Celsius takes 5 minutes to cool from 75 degrees Celsius to 50 degrees Celsius, how much more time does it take to cool to 30 degrees Celsius? Using Newton's law of cooling, minus delta T2 by delta T is equal to K into T2 minus T1. Therefore, minus delta T2 by T2 minus T1 is equal to K into delta T. Let this be equation 1. This can be written as a change in the temperature by temperature of the body minus temperature of the surroundings is equal to K into time. It is given that the initial temperature of the body is 75 degrees Celsius and its temperature after 5 minutes is 50 degrees Celsius. Since the temperature of the hot body is not constant, the average of the initial and final temperatures has to be calculated to arrive at the value of T2. When the body is cooled from 75 degrees Celsius to 50 degrees Celsius in 5 minutes, the average temperature of the body is the average of 75 degrees Celsius and 50 degrees Celsius, which is equal to 62.5 degrees Celsius. Delta T2 is equal to minus 25 degrees Celsius. Minus delta T2 is equal to 25 degrees Celsius. Delta T is equal to 5 minutes. Substituting these values in equation 1, we get 25 by 62.5 minus 25 is equal to K into 5. On further simplifying, we get K is equal to 5 by 37.5. Now, the values to calculate the time for the water to cool from 50 degrees Celsius to 30 degrees Celsius are the average of 50 degrees Celsius and 30 degrees Celsius is 40 degrees Celsius, and hence T2 is equal to 40 degrees Celsius. T1 is equal to 25 degrees Celsius. Delta T2 is equal to minus 20 degrees Celsius. Minus delta T2 is equal to 20 degrees Celsius. We need to find the value of T. (20 by 40 minus 25 is equal to K into T. On further simplifying, we get T is equal to 4 by 3K. We know that K is equal to 5 by 37.5. Substituting the value of K, and simplifying, we get the value of T equal to 10 minutes. Therefore, it takes 10 minutes for the temperature of the water to fall from 50 degrees Celsius to 30 degrees Celsius. Newton's law of cooling can be verified by conducting the following experiment. A double-walled vessel is filled with water between the walls, and the mouth of the vessel is closed with a cork through which a thermometer is inserted. Let the temperature reading be T1 degrees Celsius. A copper calorimeter with hot water is placed inside the vessel. Close the mouth of the calorimeter with a 2-holed cork. With a stirrer passing through one hole and a thermometer through the other, let the reading in this thermometer be T2 degrees Celsius. The temperature of the hot water in the calorimeter is noted after equal intervals of time. When a graph is plotted with log to the base e, T2 minus T1 along the y-axis and time t along the x-axis, based on the experimental results, we get a straight line with a negative slope.